So now we're ready to talk about the Riemann integral and demonstrate that the Darboux integral that we have studied so far actually gives us the same thing as a Riemann integral for bounded functions. And I'm going to start by giving a definition of Riemann sum. So a Riemann sum for a function p, for a function f, associated with a partition p is a sum of the following kind. Sum from 1 to n f of x I times ti minus 1, where xi is any number that belongs to the interval from ti minus 1 to ti. Okay, so that is the standard definition of a Riemann sum that you're familiar with. And so the function is Riemann integrable then. F is integrable on the interval AB if there exists a number that I'm going to write for now as R integral from A to B of f that satisfies the following property, such that for every epsilon greater than 0 there exists delta greater than 0, such that S minus this number is less than epsilon for every even sum associated with a partition P such that mesh of P is less than delta. So basically what we're saying is that if for every epsilon there should exist delta, such that if mesh of P is less than delta, then a Riemann sum corresponding to the partition P, any Riemann sum corresponding to the partition P, right, for any choice of xi's, that Riemann sum must differ from the value of the integral by less than epsilon. And so then we have the following theorem. A bounded function, so here I'm going to mention explicitly that the function is bounded. A bounded function f on the interval AB is a Riemann integrable if and only if it is Darboux integrable. And the values of both integrals coincide. Right? If the function is Riemann integral, Darboux integral, it doesn't really matter which one is which, because both will mean exactly the same thing. Okay, and now we're going to prove this. And we have to prove this in two directions. So number one, let's suppose that f is Darboux integrable on AB, and we want to prove that f is also Riemann integrable on AB. All right, so choose any partition P, right? Choose any actually, before we choose any partition P, let us let me see. Let's say it like this. So by the second criterion of integrability, for any epsilon greater than 0, right? There exists a delta greater than 0 such that mesh of P being less than delta, this would imply that U of Fp minus L, FFP, that this is going to be less than epsilon, right? So now I'm going to choose any P such that mesh of P is going to be less than delta. All right, so then I'm going to observe the following. If I take X for any xi that belongs to the interval from ti minus 1 to ti, we have now what is little m on the interval? That's infimum of your function on the interval. And what is big M? Big M is the supremum of your function on the interval. So if I take m of f ti minus 1 ti, that's the infimum of my function on the interval ti minus 1 ti. So f of xi must be greater or equal than the infimum. And at the same time, f of xi should be less or equal than the supremum of your function in the same interval, so it's less or equal than big M of f ti minus 1 ti. And from here, because this would be true on any interval, subinterval ti minus 1 ti, if I then add things up, the same inequality will hold. Add things up in the following way: sum I from 1 to n little m f ti minus 1 ti times ti minus ti minus 1. This should be less or equal than sum I from 1 to n f of xi times ti minus 1. And in turn, this should be less or equal than the same statement, but with capital M instead of a little m. And so that means this actually is the same way as saying that L of f p is less or equal than S, less or equal than U of fp. All right? Okay, so we have that. And now, so we have that, and also we know that we chose P to have mesh less than delta, so P satisfies this condition. So this is less than epsilon. Okay, so S lies between L and U, and the difference between U of fp and L of p is less than epsilon. Okay, so we also have that because, actually, yeah, because L of f is the supremum over all p's of L of fp, it follows that L of fp must be less or equal than L of f, right? And U of f is the infimum over all p's of U of fp, then U of fp must be greater or equal than U of f, right? Just by the definitions of the upper and lower Darboux integrals. And also, so let's write this as 1, 2, 3. F is Darboux integrable on AB. From this, it follows that L of f is actually the same thing as U of f, right? Okay, so now let's combine these things in certain ways here. So I know from here that U of fp if I add L of fp to both sides, U of fp is less than L of fp plus epsilon. But then from here, I know that L of fp is less or equal than L of f. So this is less or equal than L of f plus epsilon. But then also, if my function is integrable, then L of f and U of f are both actually are equal to the Darboux integral. So this is an integral from a to b of f, the whole thing, plus epsilon. And now, in a similar way, I know if I solve this equation by moving L of fp to the right-hand side, I'll get that, and moving epsilon to the left-hand side, I'll have that L of fp that is going to be greater than U of fp minus epsilon, which in turn, U of fp is greater or equal than U of f, greater or equal than U of f minus epsilon, which is the same thing as an integral from a to b of f whole thing minus epsilon. So this inequalities that I just found, and the statement about S being between U of fp and L of fp, I can now combine together. And what am I going to get? I'm going to get that S, right? S is greater than L of fp, and L of fp is greater than the integral minus epsilon. So integral from a to b of f minus epsilon is less than S. And likewise, S is less than U of fp, and U of fp in turn is less than the integral plus epsilon. So less than S, less than the integral from a to b of f plus epsilon. But then if I subtract integral from a to b of f from all three sides, and I use absolute value sign, this is the same thing as S minus integral from a to b of f, that this is less than epsilon. So what did we show? We show that for each epsilon there exists a delta, right, from the second criterion of integrability, such that whenever mesh of p is less than delta, then no matter what my Riemann sum is associated with p, this statement must be true, which means that the function is Riemann integrable and is equal to, and the Riemann integral is equal to the Darboux integral. So we're done here. And what we need to do now is to prove the second part of the statement. So we proved that Darboux integral implies Riemann integrable, so that was a proof in this direction. And so now we need to provide the proof in the forward direction. So now prove the statement going forward. So now we will assume that f is Riemann integrable on AB. Right, and if it is Riemann integrable on AB, then again I can, given an epsilon greater than 0, right? What does the definition of a Riemann integrability say? There exists a delta greater than 0, such that S minus Riemann integral from A to B of f, that this is less than epsilon, for any Riemann sum associated with a partition P, such that mesh of P is less than delta. Okay? Okay, so then now let's choose any partition P of AB such that mesh of P is less than delta. Okay? And let's do the following. So now I'm working with Riemann sums associated with the partition P. So Riemann sums, for these Riemann sums, partition points P are fixed. But the points xk I should be able to select at will, right, inside any interval. So let's select xk or xi, whatever the case might be. Let's use I. So xi inside each interval t I minus 1 ti, so that f of x I is going to be greater than capital M of f ti minus 1 ti minus epsilon. Now, why can I do this? Because what is capital M? Capital M is the supremum of f on the interval ti minus 1 ti. And the fact that it is supremum means that if I lower supremum a little bit, right, I should be able to find an element of my set which will be larger than this lowered supremum, right? Because capital M minus epsilon is not an upper bound. Okay, so I can choose capital F. You can choose xk to be like this. And so then, from this, I can see that if I take a corresponding Riemann sum as equal to the sum I from 1 to n f of xi I minus xi minus 1. What can I say about this? This should be greater than the sum I from 1 to n of these guys times xi minus xi minus 1. Right, because xi minus 1 is a positive quantity. If I replace f by something smaller, right, then the same inequality will hold. Which is now equal to I can split the difference into, I can actually open the parentheses in this expression, and this will give me two sums. One sum of the maximum of the supremum, capital M, times xi minus 1, minus, and the second sum will be just epsilon times the difference between xi's, so it's epsilon times sum from 1 to n of xi minus 1. And the first of this is nothing but the upper Darboux sum, right, corresponding to this particular partition. So this will be u of fp minus epsilon. And then if I add the lengths of all subintervals of my interval, I'm just going to get the length of the interval itself. So epsilon times b minus a. Okay, so we have that. And also, because the partition P that I chose has mesh P less than delta, also we have that absolute value of the difference between the Riemann sum and the Riemann integral. This quantity is less than epsilon, right? This is by definition of the Riemann integral. Well, okay, so then what have I got? This stuff here is equivalent to saying that S is less than the Riemann integral plus epsilon and greater than the Riemann integral of f plus epsilon, right? Just simply getting rid of the absolute value sign and then adding Riemann integral to both sides, that's what I'm going to get. All right, so S is less than this, less than the integral and greater than the integral. Plus and minus epsilon, actually there should be a minus sign here. All right, so then what can I conclude from these two statements? Then what do we have? So let's look at the first relationship that we found, that S is strictly bigger than this, right? If S is bigger than this, then I can solve the inequality, right? So S is greater than this difference. I can solve this inequality for U to get that U of Fp is going to be less than S plus epsilon times b minus a, right? That just follows from this inequality by adding epsilon times b minus a to both sides. Well, and then I know that S is also less than the Riemann integral plus epsilon. So this is less than Riemann integral on the integral from a to b of f plus epsilon plus epsilon times b minus a, right? I simply replaced this S by that expression because I know that that expression is bigger. All right. But also in addition, one more thing that I know, and that is that U of f, the value of Darboux, upper Darboux integral, this is an infimum of U of fp's. So this U of fp is greater or equal than u of f. But this is a theme, going to be a common theme when we establish different properties of Darboux integrals. We're going to heavily use the fact that upper Darboux integral is an infimum of upper Darboux sums, and lower Darboux integral is a supremum of lower Darboux sums. So now if I examine what I have gotten here, I have this number, which is independent of a partition P, and I have this number, which is also independent of a partition P. So what we got is, now, when I did my calculations, I chose epsilon and I did these calculations, but my end result is independent of epsilon. So what I got is that u of f is less than the Riemann integral plus epsilon times b minus a. This is true for every epsilon greater than 0. But if it is true for every epsilon greater than 0, I can make epsilon as small as I wish. So if I send epsilon to 0, if I take a limit of this as epsilon goes to 0, independent of epsilon, this goes to 0. So in a limit, I have that u of f is going to be less or equal than the Riemann integral from a to b of f. Okay? Now, in a similar way, we can also show that L of f, right, basically just operating with L of fp in exactly the same fashion, we can show that L of f is greater or equal than R, than the Riemann integral from a to b of f. But we also know that u is always greater or equal than L, right? That upper Darboux sum is always, upper Darboux integral is always greater or equal than lower Darboux integral. So therefore, what we got is that R from a to b f, right? That this is less or equal than L of f. L of f is less or equal than u of f. And u of f in turn is less or equal than the Riemann integral, R from a to b of f. Right, and from here, because the lowest thing and the largest thing are exactly the same, it follows that everybody here is exactly the same. So therefore, L of f equal to u of f is equal to Riemann integral from a to b of f, right? And L of f equal to u of f means that our function is Darboux integrable, right? And that the Darboux integral is equal to L of f and u of f, so therefore integral from a to b of f is the same thing as a Riemann integral from a to b of f. And so we're done. So that means that effectively, for bounded functions, Riemann integral and Darboux integral are exactly the same thing. So if I now am going to prove some properties of Darboux integral, all of those properties should apply to a Riemann integral, because for bounded functions, those are exactly the same things.